So in the first speaker of this session is Israa Othman. She works in the chemistry department of Khalifa University, Abu Dhabi. She will be talking on tailoring the synthesis of platinum and graphitic carbon nitride quantum dots deposited on copper iron oxide microspheres for CO2 photocatalysis reduction to high-value products. Go ahead, Israa.
Good morning, everyone. Today I'm presenting part of my PhD work, which focus on the use of quantum dot-based nanocomposites for CO2 photocatalytic reduction. So, starting with the major issue, which is greenhouse gases. They contribute to the global warming, as CO2 by itself contributes to 50% of the radiative forces causing the increase in the temperature of our atmosphere. So it was estimated that CO2 concentration was around 1.3 million megaton in 2017, with atmospheric concentration around 410 ppm. So CO2 emission from petrochemical industry was around 500 million megaton, 500,000 megaton. Among these companies, of course, we all know ADNOC, it contributes actually to 13,000 megaton of the total emission. So what we're aiming, what we have to do is we need to reduce CO2 emission by at least 50% to prevent an increase in 2% of the temperature of our planet. Some of the approach that are used includes using green fuels and alternative energy sources. In addition to that, the more obvious solution is through CO2 capture, sequestration, and utilization. UAE has a vision for 2050 that aims to reducing CO2 emission to zero. It was already started back in 2017, and so far there was an obvious decrease in CO2 emission in the country. Some of the other approaches that are commonly used for CO2 mitigation are converging CO2 to different products. In industry, it is done through different processes, such as we have thermochemical methods, subtire, reverse water gas shift, and hydrogenation, which is the one that I'm focusing on in this work. So hydrogenation basically aims to reducing CO2 by reacting it, by using hydrogen to form different products such as hydrocarbons, methane, and oxygenates. Some of the approaches that are used include electrocatalysis, enzymatic techniques, and the one that we used in this work, which is photocatalytic reduction of CO2. And as I mentioned earlier, I'm mainly using quantum dot-based nanocomposites. For those of you who are not aware of what quantum dots are, I'll give you an overview, even though we all know that last year quantum dot discovery won Nobel Prize. So in general, quantum dots, they are particles which are very small in size. They have quantized and discrete energy levels. They're referred to as artificial atoms. The main property that sets them apart from other nanoparticles is the quantum confinement effect. So the quantum confinement effect states that the particle diameter has to be less than the exciton Bohr radius. This contributes to one of the main properties of quantum dots, which is the band gap size relationship. So as the quantum dot size decreases, the band gap increases, and as the particle size increases, the band gap decreases. This property, along with the large surface area to volume property, it is easy to tune their band gap, and their high PLQY made them used in many applications, such as in biosensors, in energy conversion, in displays, in LEDs, and in many other applications as well. So in this work, we mainly aim to design a photocatalyst that has high efficient photon absorption, highly selective for CO2 absorption, has high selectivity toward forming C2 and C4 products, has visible light activity, has a dual functionality because we're using water as a medium, so we need to generate hydrogen first and then use it to reduce CO2. And finally, it should have a good conversion yield. So the system that we proposed is copper ferrite with graphitic carbon nitride, the quantum dots, and silver nanoparticles. We did different characterizations for the nanocomposites, starting with the XRD. We observed the diffraction planes assigned to cubic copper ferrite, and the diffraction phase related to graphitic carbon nitride with a slight shift in the 002 peak, which was due to the lattice compression. And then in the Raman, we observed the Raman modes assigned to copper ferrite and the D and G bands related to graphitic carbon. Then in the BET, we found that as we increase the loading of the quantum dots, we increase the surface area of the nanocomposite as well. And finally, here in the FTIR, we observed the vibration modes for copper ferrites in the fingerprint region, and the CM bond assigned to the graphitic carbon nitride. And we noticed that as we increase the loading as well, we increase the intensity of the CN bond. Then we did high-resolution TEM for the silver, for the nanocomposite with the silver. So as you can see here, the large spherical particles are copper ferrites, and on the surface, we deposited the graphitic carbon nitride quantum dots. From measuring the D spacing, we observed the 002 crystal plane assigned to graphitic carbon nitride, and we observed the crystal planes assigned to copper ferrite as well. From the selected area electron diffraction, we matched the crystal planes with the ones we found in the XRD, so that confirms the presence of the cubic phase of copper ferrite. Then we conducted XPS to determine the chemical environment and the oxidation state of the elements. So for copper, we found that we have metallic copper. For iron, we have iron +2 and iron +3 environments. For oxygen, we have oxygen -2 and oxygen -1 environment. For the carbon, we have carbonyl, carbon-carbon double bond, and carbon-carbon single bond. While for silver, we have metallic silver and silver oxide. Then I'll move on to the photocatalytic application part. So we used a glass reactor where we added water. We bubbled CO2 in the reactor and irradiated the system with visible light. Then samples were collected in specific intervals and analyzed. First, we started with the hydrogen evolution. We found a concentration after 5 hours was around 2.5 micromole per gram. So then we know that the quantum dots we managed to produce hydrogen from the quantum, just from using the quantum dots. Then we tried different concentrations for the quantum dots, and we formed different products, mainly formaldehyde and acetaldehyde and acetone. And the highest concentration we obtained was 14 micromole per gram using this concentration, and it was highly selective for formaldehyde. Then we tried the effect of using different wavelengths. We tried the UV at I cannot see it clearly actually, 265 nanometer, and visible light. And then we found that when we use this wavelength, we have higher yield of acetaldehyde. Then we moved on to testing the copper ferrite microspheres. So we did the reaction in dark condition and illuminated condition. So in the dark condition, no products were formed, while in the illuminated condition, we formed acetaldehyde. Then based on that, we decided to prepare the nanocomposites by depositing the graphitic carbon nitride on the copper ferrite using different ratios. And then we observed that as we increased the loading, we produced higher yield of acetaldehyde in addition to acetone and methanol as well. The final stage was using the nanocomposite that gave us the best performance, and we deposited silver nanoparticles on the nanocomposite, which doubled the yield, and we ended up forming 84 micromole per gram of the of acetaldehyde, in addition to methanol, acetone, and formaldehyde. So, based on the obtained products, we deduced that the most probable mechanism would be the glycoxyl mechanism, which yield C2 products. Based on electrochemical characterization and UV, we constructed our theoretical a band structure, and we're assuming that Ag will act as an electron sink in this structure, and this is so far we're still in the studying the mechanism, so the work is not finalized yet. So in conclusion, we successfully prepared different nanocomposites, characterized them using different techniques, and tested the CO2 conversion using these nanocomposites. We observed that under ambient conditions and using water and visible light irradiation, we observed the formation of acetaldehyde, and the catalyst was highly selective toward forming acetaldehyde. Thank you.
Thank you, Israa. So there's no time for the question, sorry. So